Hi everyone, welcome to the session on data structures and algorithm. Session on the sets, which is 3 2, and this follows the stacks and the queue session. We are uh, pre-recording this, and we'll be uploading this and removing the old one because of some uh, voice issues we had, and hopefully you can understand recording issues. With that, I will hand over to Jaimit Vasawa, who is continuing on the session of sets. Welcome, Ayushi, Angla, and others who joined. Thanks. Go ahead.
So, hello everyone. My name is Jamit Vasawa, and thanks for the introduction. So, we'll start with the DSA's session 3.2, which, as Prakash mentioned, that we are recording it again on sets. So let's get started. So, what are sets? Sets are unordered collections of related members in which no members occur more than once, which means they only contain unique elements and they do not care about the orders in which they are appearing. But each and every element has to only occur once. So some of the applications of sets are data correlation, determining interesting relationships between sets of data, then set covering, an optimization problem that nicely models many problems of combinatorics and resource selection. Then mathematics with sets, specifically combinatorics and probability. Sets have their own principles and rules that computer help apply. Then graph data structures typically used to model problems defined in terms of relationships or connections between objects. Then graph algorithms that solve problems modeled by graphs. And relational algebra, the theoretical query language for database systems. So fundamentally, the set theory forms the basis for all the query languages. So let's just see an example of sets with regarding to graphs. So these are two images, A and B. As you can see, there are some differences in the set. The image A is a directed graph. You can see the arrows being used, and the set and image B is an undirected graph. So graph is a pair of graph G is a pair of V and E, where V is the set of vertices here 1, 2, 3, 4, and E is the relation or binary relation on V. So graphs are composed of two elements or two types of elements, which are vertices and edges, as we saw. Vertices being 1, 2, 3, 4. So graphs are represented in form of a pair of V and E, which is vertices and edges, and you can see the relationship of it being an ordered pair of UV, where E contains the ordered pair of UV, where V is a set of vertices 1, 2, 3, 4, and E is an ordered pair or a set of ordered pairs, and in the directed graph, I'm talking about the image A. So E will be as one arrow is connecting to 2, 3, and 4. So 1, 2, 1, 4, and 1, 3 are the ordered pairs for 1. Then 2 is connecting to 2 and 3, 2 and 4. And then 3 is connecting to 2 and 4. And 4 is not connecting to anyone. So these are going to be the ordered pairs. So as you can see in the directed graph, we have listed it for the ordered pairs of E. Then for the undirected graph, the edge between UV and VU are same, are treated as same. So V remains the same, 1, 2, 3, 4. The E is a relation of one node to another. So two important relations in graphs are adjacency and incidence. So adjacency is a relation between two vertices. If a graph contains the edge uv, vertex v is said to be adjacent to vertex u. In an undirected graph, this implies that vertex u is also adjacent to vertex v. In other words, the adjacency relation is symmetric in an undirected graph. This is not necessarily true for the directed graph. Now, this was just a small example for the graph, for the sets and its implementation on graph. So let's continue with the explanation on sets. So these are some of the basic definitions, operations, and the properties that we will be discussing for some time. So S equals to U is basically the universal set, and S equals to S equals to U, and S is equals to null set is an empty set. S equals to U is the means S is also a universal set. And you can see the examples of it. Same going to point 2, S1 equals to S2 means S1 and S2 are equal, and S not equal to S2, S1 not being equal to S2 means they are not equal, and you can see the differences in the examples B. Then S1 is subset of S2 means S1 is a you can see the example of S1 and S2 and S2 and S1 where S2 is not the subset of S1. Then basic operations of sets S1 union S2. As you can see in the example, it consists of all the members of set 1 and set 2, which is 1, 2, 3, 4. Then S1 intersection S2, where the common element of both the sets, which is 3, so 3 is given. Say for S1 difference S2 or S1 minus S2, the elements containing the members of S1 and except those of S2. So you can see the difference of intersection and difference here, where S1 minus S2 results in the elements 1 and 2. Next up, these are some of the properties of the sets. The intersection of a set with the null set is null set, and a union over null set is the set itself. Then the intersection of set with itself is the set itself. Same is for the union. Then S1 intersection S2 is the same as S2 intersection S1, and same for the union as well. Then for the fourth, which is the associative law. So S1. So let's just see the intersection, the fourth point 1, with the help of an image. So you can see the starting from left to right, we have S2 and S3's area or intersection. Then S1 being counted in, and then it's the same thing as S1's area being S2 with the 3 being counted in at the last. So it basically means the same in whichever order you do. Same is for the union as well. Then fifth is the distributive law for the sets containing S1, S2, S3. So and also you can see the solution, an example of it, where set S1, S2, and S3 and their what are the elements that comprise of them, and the LHS and RHS for both A and point A and point B. Continuing with the sixth point, which is And these are most of the calculative ones, so I can't read over them, but you can see the examples being calculated and proved the, proved with the example, with the help of the example. The seventh one is the property of the set and distribution. Same, the LHS and the RHS of both the sides of the equation has been proved with the help of the set examples. So now, as we have discussed sets, now we'll see how we will be implementing the sets. And we have discussed the linked list first and at the beginning of the DSA sessions. So these are the this is the same implementation of the linked list that we'll be using for the set as well. So as you can see, the type def list set is used, which means that set is definitely similarly going to be executed as a list. And on the right section, you can see the list element, which is the part of the list.h or the header files of the list where we have defined the list and its structure is being used. Here, just for the example, we on the right we have we can see the initiation of the set and its argument with the help of the function pointers, and the set with the set pointer and the function pointer of match, which takes two arguments, key 1 and key 2, basically to compare the two elements of the same set. This is done because of different reasons, like if you want to see whether two elements are equal for insertion, removal, traversal, etc. Then destroy function for the deallocation of the memory that we'll be using. So these are some of the interfaces that we'll be using, and you can see how they are defined. I will just go through them for their use. So set initiation is initiation of the set, which takes, as you have seen, as I just mentioned in the previous slide, that it takes set pointer of set struct, then a set structure, then it takes a function pointer match for taking two values, and the destroy function for deallocating the memory. Then set destroy is for destroying the element or deallocating the element. Then set insert for inserting the element, set remove for removing the element, set union, set intersection, and set D. These are the common operations we just saw about the set. So those operations will be done with the help of set U, set I, and set D for union, intersection, and difference, by comparing the other two arguments of set 1 and set 2 for all three of them. And then all the other one are set is member, set is subset, set is equal, and set size, which are in a way self-explanatory, where a set is member checks whether the the element is member of the set or not. Subset checks for whether the set is subset of the another set or not. Set is equal checks whether the set is equal to it or not. Then set size gives the size of the set. So this is one of the implementation of the header files of the set, starting with the from of course, from going from the left to left segment to the right segment, starting with the left, we have the standard library and the list.h that we have been using. Then we define the list. It's the same that, and all the structures being listed out in form of .h file for the use of in the C program. Then this is the actual set.c file or the C program that we'll be going through. Okay, so as displayed, and that this is the whole set.h file, and which contains our initiation of the set and everything that we need for the implementation of the set.c file, the insert, the remove, and the union, intersection, and difference operations of the set, then member, subset, equal, and size. So starting with the actual C, the .c file or the implementation of set.c. First, we have the initiation of the set, and as you remember, we are using set with the help of a list. So we are using list init. Then for the insertion of the elements, as it is a set, we do not allow the insertion of the duplicates. So this is what it checks for. And then if it is not duplicate, with the help of list insert next, we'll be implementing the inserting the data. Then for removal of the data, we'll be using set remove, and then find the member to be removed, and if the member not found, the removal is not possible, and give us a but if the member is found, then we'll be using list remove next for for removal of it. Then for a union of two sets, as mentioned before, the set U for a set union will be done, which will be taking the elements of set 1 and set 2 and storing it in set U. So first we'll implement the initiation, where a set U will be filled with every member of set 1. Then after checking the for the duplicates, set 2's element which are not present, as no duplicates are allowed, will be stored in set U. But for some reason, if there is a failure, the set U that was created will be destroyed, and for the unsuccessful execution, it will give us the -1. Similar kind of execution will be done for the set intersection, where we'll first initialize the set I for the intersection of set 1, and set 2. Then after checking the values of set 1 that are present in set 2 and taking it, we'll be inserting the common elements at the tail of set I or at the end of set I. And if just in case the execution is not good, then set I will be execution is a failure, then set I will be destroyed, and -1 will be returned to us for its return to us. Then we have a set difference, which basically gives us the member of first set that are not present in second set. So the way we will be implementing it is first we initialize it for set D, then for checking its member of set 1, as you can see that we have first implemented this, and then after that for checking the members of set 1 and set 2, we'll be using set is member function and then not operator, so in order to implement it. So whichever element which are not the member of 2 will be checked for, and in the end, with the help of a list insert next, we'll be adding all the elements of difference in set D. Set is member as it checks for the elements whether the given element is in within the set or not, and it does with the help of set match and match function, taking into our arguments the data and the list data member for which is defined for traversing the set. Next is checking of the set is subset or not. First it will just do a quick test as if a set is asked whether it is subset to other set or not, then it cannot be if a number of elements are greater than what it is asked for it to be subset of. So that is what it is checked. If one has more set 1 has more elements than set 2, then it cannot be a subset of set 2. So in that case, it will check for this, and if it is, then no. And if it's not so, then we'll then use similar to before. We will be using the not operator here, and with the set is member. Next is to check whether the set is equal or not, and similar kind of checking will be done for as we have done for the set is subset. For set is equal, also a similar kind of check will be done, as if the size of the sets are not equal, then it cannot be equal, or the number of elements in the set are not equal, it cannot be equal. And if it is, then with the help of set is subset, we'll be returning it. So yeah, we went through this program and what most of the blocks basically does through it. So next is an example of a set data structure using a greedy algorithm approach, where we are looking through a skill of a set S, which comprises of skill and having the elements A through L in it. Then another set P, which comprises of players, and each and every player you can see that possesses some of the skills that are present in set S. What we have to cover in set C is that every element every element from the set S has to be covered, and with as minimum of the players as it can be. So you can see the optimal covering for set C is A123, and some of the derived solution for greedy algorithm approach contains player A6 also. with A1, 2, 3. So you can see diam a diagrammatic approach to the sets that are being covered. First, we have A6 being covered, then we have A2, then A1, then A3, which covers all the elements in the end by code. So let's see the program to it which covers it. So these are the components that we'll be using. The K set is used for the subsets, uh, and cover is so. Let's just for the for the given program, members will be skills, subsets will be the players, and covering would be the final set C, where will be all the covered skills with the players will be stored in, and we'll be we'll be using K-set for covering the sets subsets. So these are the header files that will be used. Standard is the normal header file, then cover.h, we just saw this.h and set.h. Set.h we just saw in the beginning of this session. Then first we will initialize the cover for first we'll make it and then initialize the covering, where and here where it is been defined, we'll be using member and max member. Max member basically means that how many members have been covered or how many skills have been covered, skills in context to this very program or the context that we are discussing. So we'll be starting with the max size, which is with its value as 0. Then as we will be iterating through the members of it, we'll be adjusting the size, its value. So yeah, first we'll be covering the we'll be finding the subset that covers the most members, and then adjust the size of the max size that we initialize with 0. But if there is no intersection possible, then there is no covering possible, and hence it will end. But if there is a covering possible, then we'll be inserting the subsets or the set of players into the covering with the help of set insert. Then after inserting and iterating through each and every element, we'll check whether there are any set of skills remaining in the main set or not to be covered. If it is, then we'll be only checking here whether the set of skills or the set of members are still yet to be covered or not. And here we'll be checking the with how many players are covered, and if in the end there are still remaining members or the skills, that the condition that we have covered over here If there are still still members to be covered with the given subsets or the given players that we have, then for the given players it is not possible, and that's why it's also written that no covering is possible for here, and it will give us the um, give us -1 for fail to cover all the skills with the given players or all the members with the uh, given subsets, and hence it will give us the failure if it fails to cover. And if just in case we are able to cover with every element, then it will give us it will give us the exit code 0 for its successful execution. So these are some of the references, but before that we'll go to some of the question and answers that might be there, as how and why it can be done, or what might be the different way to do it. So first is, instead of implementing the set subset as shown, how could we use other set operations to determine if one set S1 is a subset of another? So as you can see that uh, we can we can use a set intersection and set is equal, which are not as efficient, but the same execution can be done with the help of those two. And you can also see the time complexity differences between both of them. Then next, instead of implementing set is equal as shown, how could we use other set operations to determine if one set S1 is equal to another set S2? So it is, so you can see that we are able to achieve it with the help of calling two set difference function and two set size function. Although less efficient, but we can still do it if we don't want to use it for set is equal. Then question 3 is, instead of implementing set intersection as shown, how could we use the set difference operation to compute the intersection of two sets S1 and S2? So you can see it uses a set difference operation with the help calls. It achieves it basically with the help of two set difference calls. Then why was list insert next used instead of set insert to insert members in the sets built within set union, set intersection, and set difference? So set insert next basically checks for each and every element going through the list, because we do not have to allow duplicates in the set, and that is the reason it will have the big O of n complexity compared to the intersection, union, and difference. Yeah. Then this is a numeric. The question 5 is a kind of a numerical one, but you can see the for the given sets and for the given steps, the operations that are being taken place. Same is a kind of similar thing for question 6, which uses the which just states as a numerical and asks us to use the properties and basic operations presented for the sets. The third one is the symmetric difference of two sets, which basically means what are the elements that are not present in either one of them, and how we can achieve it is as the symmetric difference of S1 and S2, or S1 delta S2, is done with the help of union of S1 minus S2 and S2 minus S1. And for the example, you can also see that if set 1 consists of 1, 2, 3, and set 2 consists of 4, 5, 6, But for this, we'll be for as it is set, and we are not having any duplicates. So what we can do is directly have the contents of S1 minus S2 and S2 minus S1 in the set union operation, set union set, or any kind of set where we can store its a union. Then a multiset. So a multiset is a type of a set that allows the members to occur more than once. So how would the runtime complexities of inserting and removing members when a multiset is compared to with the operations for inserting and removing the members, which is so for set till now we have only discussed the insertion and removal operations where only an element occurs single time. But multiset is a concept where the elements are allowed to occur more than once. So for that, so removing a member from a set is big of an as well, because we may have to search the entire set again. In a multi-set, inserting a member is considerably more efficient because we do not have to traverse the members looking for duplicates. So therefore, we can insert the new member in big of one time. In a multi-set, removing a member remains a big of an process because we still must search for the member we want to remove. So you can see the difference of the insertion in multiset and insertion removal of in multiset. For multiset, we have the time complexity of big O of n. So these are some of the topics for the sets, and these are the references that we that are being used for these PPTs. So thank you.
Yeah, well done. So there is a Q&A at we presented, so people can go through them. And thank you for the presentation. I think we can end the session here. Ayush has left, and they can see the records. Suraj can also refer to the records. I'll stop the recording.